Welcome back. In the previous recording, I introduced the concept of vectors. I said a vector quantity, or just a vector for short, is any physical quantity that has both magnitude and direction, and you need to know both of those things in order to know everything there is to know about the vector. And I gave a number of examples: linear position, and force, and acceleration, and weight is another one, although weight is actually a category of a force, but never mind that. Anyway, lots of different things are vectors, and where if you don't know the direction that the physical quantity is pointing, you don't know everything about it. And so contrasted with that are quantities that are scalars, and they don't have direction. Direction is meaningless, okay? And I actually started to say something in the previous video, and then I distracted myself on it, so let me say it here while I'm talking about scalars. I mentioned that when I was giving this example, I said I started from home and I traveled 4 kilometers north to Starbucks and 3 kilometers east from Starbucks to school. And so although I traveled on the road 7 kilometers, my actual net distance from my home is only 5 kilometers. And I mentioned that the distance that I actually traveled, the 4 kilometers here, 3 kilometers there, is the magnitude of the vector, and doesn't have the direction linked to it. The 4 kilometers by itself isn't part of the direction. Okay, the direction is north. Okay, so 4 kilometers, which means, by the way, and this is what I was getting to, is that 4 kilometers can be, and indeed is, considered to be a scalar quantity. In short, the magnitude of any vector is a scalar value, and the direction is independent of the magnitude. And so the magnitude of any vector is, in fact, a scalar quantity. Okay, we will use that fact a lot. All right, and so then out that since 4 plus 3 is definitely not equal to 5 in ordinary numbers, then vectors evidently obey a different set of algebra than ordinary numbers, so then the different set of algebraic rules than scalars obey. And so my upcoming purpose is to teach you the algebra of vectors. Okay, and I mentioned that of the differing mathematical rules, we need to make it clear in any equation that you write that you are in fact dealing with vectors. And so I talked about putting little arrows above the symbols to alert yourself and your reader that you're dealing with vectors. And I said that this expression here, as I've written it, these 3 expressions are incomplete as they stand. And the reason is basically what I was just saying. The left-hand side, by putting the arrow symbols, that's a claim. I'm saying D1 is a vector quantity, and obviously it is. But the problem is the right-hand side of this equation, of this equality, is only a scalar. There's nothing on the right-hand side that has anything to do with direction. It's only 4 kilometers, which, as I just said, is a scalar. So, but an equal sign means that the left-hand side and the right-hand side are the same thing. They're entirely equivalent. These can't be. If the left-hand side is a vector, as indicated by this symbol, then the right-hand side has also got to look like a vector. So we're missing a symbol on the right-hand side, and we need to do that. Now, the most obvious thing to do would simply put an arrow directly above the 4 kilometers, but that's not what is done. We actually have something else. And then what it is we do is actually going to take me quite a little while to explain. Okay? So let's get to it. I'm going to reproduce this diagram over here. Getting a little too crowded. Okay, so this is kind of what we're working with here. Okay, so I'm going to leave out the symbols for the house and for Starbucks because they're not relevant for my present purposes. Okay. I trust, by the way, that it is evident to you why that's equal to 5 kilometers, where that came from. And if it isn't evident, I'll point out that this construct here, because I traveled north and then east, and north and east are perpendicular to each other, I've constructed, of course, a right triangle here. And so a 3, 4, 5 right triangle, in fact. All right. Pythagorean theorem, if you prefer, which I do. Okay. Now, the trick I'm going to pull here is I'm going to impose a Cartesian coordinate system on this collection of vector arrows. I will have a great deal more to say about coordinate systems in days and weeks to come, but for now, I will simply say that I have the freedom to put my coordinate system anywhere I want to. There's a couple of rules, but briefly, but for now, I can do pretty much anything I want. I have near complete freedom to choose and draw and place my coordinate system. So I'm going to make a fairly natural choice, and that is I'm going to put the origin of my XY coordinate system at the starting point of my journey. Okay, so I'm going to have my x-axis point this way. I'm going to have my y-axis point this way, and let me be a little bit clearer. I put the little arrowhead on the axis, and the meaning of that, let me start that sentence over again. I put my arrowhead on the coordinate axes only on one end. I didn't put it on both ends. Okay? And the interpretation of that is whatever direction you put the little arrowhead is the direction of increasing positive values. Okay, the values are getting more and more positive, closer and closer to positive infinity in both directions. Okay, so that's how you know whether you're pointing in the positive direction or in the negative direction by where this arrowhead is indicating. So this arrowhead indicates the direction pointing towards positive infinity always in both directions. And in the z direction too, when we eventually go three-dimensional. In any case, now I can look at this, and now I can say something new. Now that I've put this coordinate system on top of things, I can say not only did I travel 4 kilometers due north, but I can instead of saying due north, I can say I traveled 4 kilometers in the positive y direction, and I traveled 3 kilometers in the positive x direction. Okay? And that's reasonably useful. Or it would be if I had some way of indicating that in this equation. And I do. And this now is yet another bit of vocabulary for you here. And I'm going to introduce some new notation here. I'm going to say, okay, I am going to, let's see, I'll stick with black, I guess. I am going to say, if I have a vector that points in the x direction, then I'm going to use a label, a symbol, a letter that represents that. And like this. I circumflex, or but circumflex is too many syllables and too hard for me to pronounce, and this is known as, instead of calling it circumflex, we'll call it a hat. Okay, and so this is called I hat. And in fact, I never actually write the little dot above it. So I hat suggests indicates the positive x direction. And related to that is j hat, which implies the positive y direction. And since we're here, although we're not going to use it for a little while, but I'll toss it in there, k hat, I bet you can guess already, is a symbol that indicates the positive z direction. What do I mean by all this? What I mean is, these three symbols, as it will turn out, by the way, I'll give you a heads up, as it will turn out, these three symbols are actually vectors. They have magnitude and direction, but for the moment, let's just treat them as symbols, and they mean something. They mean the positive x, y, and z directly, okay? So what do I do with them here? This is how you use them. I'm going to put them in my equation here in red just so they stand out, not that there's any significance to the color. Okay. Well, this 4-kilometer leg of my journey, as I said a moment ago, happened in the positive y direction. So what I'm going to do is write 4 kilometers times j hat. This is actually a multiplication. Okay. And the 3 kilometers is in the x direction, so I will multiply this, attach to it an I hat. Okay? And as for the 5-kilometer vector, as you see, it doesn't point in either the x or the y direction, or the z direction either. And so I'm going to give it kind of a similar symbol. And I'm going to use n hat, implies any other direction. So we save the symbol n hat for when the direction that my vector is pointing is not any of the 3 cardinal directions, x, y, or z directions. So if we don't know for sure that it's pointing in one of those 3 directions, we don't use I, j, or k, we simply use n. And this is not the last that you're going to hear of these objects, but for now. And so then I would write n hat here. So what have I gotten? Well, I have this scalar quantity multiplied by that direction, well, multiplied by j hat, this scalar multiplying by I hat, this scalar multiplying by n hat, okay? And indeed, I can finally now fix my notation over here in exactly the way that I just did over there. D1 is 4 kilometers j hat, D2 is 3 kilometers I hat, 5 kilometers n hat. And now these are indeed correct equations, correct equalities, because both sides now have vector notation. Because we have magnitude here and we have direction indicated by these hatted objects. Okay, so the purpose of the I hat, j hat, k hat, and n hat things are to indicate the direction that some vector is pointing. Which is great and it's fine, but actually there's more to these vectors than I've said so far. So let's, wait a minute. In fact, I just gave the game away. Actually, I said it earlier too. These things here are not simply indications of direction. They are, in fact, vectors, complete vectors in and of themselves. Okay, so let's talk. If I'm going to claim that these are vectors, and I am, then they're obliged to have the same properties that the other vectors I've talked about have, which is they have to have both magnitude and direction. Well, I've already used direction, there they are. As for the magnitude, That's actually a matter of definition. So their purpose, as I just said, is to indicate the direction that some other vector is pointing, and that's how we used them over here. I said that I hat indicates that this vector d2 is pointing in the positive x direction. And this construction here then, how I interpret it is I say, okay, d2 is a vector. I can tell because it's got the little arrowhead above there. And its magnitude is 3 kilometers, and its direction is in the positive x direction because that's what I is defined to mean. By the way, did you already pick up on this? I, J, K, X, Y, Z, alphabetical order matching? Okay. So that's fine, but if D2 is a vector, and it is, and since I'm claiming or indeed defining it to also be a vector, which is okay because 3 kilometers, the 3 kilometers is only a scalar, so it doesn't change anything about the nature of the vector. It's only an indication of the magnitude of D2. What that means, though, and here comes the thing, we knew ahead of time that D2 is 3 kilometers in magnitude. So if I take 3 kilometers, multiply it by I hat, and I get a 3 kilometer vector back out again, well, that means that the magnitude of this vector has to be only 1. Right? Because I'm taking 3 kilometers, multiplying by this vector. If this vector were anything other than 1, then I'd get a vector. Suppose this vector were 2, right? 2 what? I don't know, 2. Then multiplying 3 kilometers by 2 would give me a 6 kilometer vector, but that's not what D2 is, right? And so, anyway, but that means that this vector is exactly 1, okay? And 1 without any units either, because I can't change the units of my, a length has units of kilometers or meters or whatever. And so multiplying by this vector can't change the units either. And so the magnitude of I hat and of j hat and of k hat and of n hat are all, the magnitudes of these vectors are all identically 1. And that's part of their definition, in fact. The triple equal here means actually that it's defined to be, rather than it's just an equality, it's actually a definition. It's a choice rather than a calculation. Okay, so all of them by definition have a magnitude equal to 1, all right? These objects are known collectively as unit vectors. The word unit in this context referring just referring to the number 1, the magnitude of the thing. Okay, it's not referring to the units of whatever physical quantity you have in mind. No, the word unit here simply implies 1, the numeral 1. Okay, so unit vectors then. They're used all over the place, all the time in physics, and I'm going to use them a lot starting almost immediately. Okay, so you want to get very comfortable with them very quickly. I will show you basic usage of these things, and I'll teach you how to deal with these, along with all the vector algebra that I'm going to be teaching that applies to all vectors. It will apply, everything I teach you about vector algebra will apply just as well to these unit vectors as they do to any other kind of vector. And there are some special considerations for unit vectors when doing the vector algebra. But whatever those special considerations are, they're not, it's not that the unit vectors behave mathematically differently than any other vectors. They don't. The unit vectors are calculated with and on exactly the same way that all other vectors are. And in fact, any vector, every vector, can be written as some scalar value multiplied by one or multiplied by, let me start that sentence again. Any vector at all of any kind, no matter what, can be written as a combination of a scalar value times I hat plus some other scalar value times j hat plus some other scalar value times k hat and perhaps some other scalar value times n hat. Okay, and we will see more of that. And so don't sweat it right now. At this instant, the twin concepts I want you to get is just the idea that these particular kind of unit vectors exist, how they are defined, the directions that they point, and the fact that every one of them by definition has a magnitude of identically 1, and how we are, and the beginnings of how they are used in other equations. And the answer is this vector here is represented by this scalar multiplied by this unit vector plus and then this vector is this magnitude multiplied by that unit vector, and this one in this way. Okay. All right. That seems like a good stopping point. Let's stop there, and then maybe next recording we'll start actually doing algebra.